Thank you very much, Juan, and also the other organizer for the invitation. And thanks also for a very kind introduction. So today I'm going to talk about a broad framework of data-driven optimization, data-driven decision-making, and in particular, a couple of research questions that emerge in this context. And then I'm going to focus on one of those. So let's get us started. Okay. And by the way, feel free to interrupt me at any time. It's no problem at all. So my talk has two parts. So the first part is a little bit, let's say, the broad overview is a personal view that I got over the last 5-6 years about the topic of data-driven decision making and several different communities that are working on. I particularly talk about a framework, a modeling framework known as distribution robust optimization, primarily developed in the operation research community. And then I want to highlight 3 different research questions that typically pop up there. And then I focus on one of them known as online optimization or online convex optimization. And this, let's say, subtitle that you see is the takeaway message that I hopefully get across throughout my talk. So, okay, let's start from how we see this data-driven decision-making and problem description of that. So in any decision-making, you can think about 3 fundamental ingredients. And by the way, I hope you see my cursor, right? Okay, great. So basically, we always end up with 3 ingredients in any decision-making problem. So the first one is the decision that we get. Throughout my talk, I'm showing it with the X variable. Then we also have some uncertainty that we typically do not know exactly at the time of the decision. I show it with this psi variable. And usually from a mathematical perspective, we treat it as a random variable whose distribution describes its behavior. And then finally, in all the decision making, there is a loss function that we care about. The loss function is a function of these 2 variables and deliver some R value. And that's how we measure our satisfaction about decision making. Now, speaking of data-driven, what happens more often than not is that we don't have access to this data-driven, this random variable distribution. What we have instead is a bunch of previous realizations. And we want to make a decision based on these realizations. And that's represented by the first arrow that I have here. So you can think about the data that you collected in the past as a past, and this, let's say, psi1 and psi-n are realization of this random variable. Then you make a decision that you can think about it, what is happening in presence. And now when we are speaking about performance, what we are particularly interested in is not the performance of this decision on the past data that we had seen, but more about a new unseen realization that revealed to us once we make a decision. That's somehow represented here by future. So the loss function evaluated on our decision and some unseen data point. And that's what we are interested in. So let me give you a very classical toy example to show the meaning of each of these objects. So think about a very typical curve fitting problem. It's a very old problem that we have a bunch of data points and we want to fit a curve to that. So you can think about these data points are just a bunch of data in this particular example, 2-dimensional data. We want to fit a, let's say, hyperplane to this data point. So speaking of decision, you can think about how we basically parameterize a 2-dimensional hyperplane. And that's the decision that we want to make based on this data point. Now, when you talk about the loss function, you can think about these values as the, let's say, the mismatch between the curve that we fit to the data and what we actually wanted to describe. So these are the loss function evaluated on the past data point. But these are not, as I mentioned earlier, our particular point of interest. What we are interested in is that what happened now if a new data is generated. So if a data generated, what would be the loss function evaluated at this new data point? So this diagram that I'm picturing here is a very old and classical picture of data-driven decision-making, and there are different communities working on the different subjects of this picture. So perhaps what we immediately connect to that is machine learning literature. So in machine learning, I would say each of these components get a little bit natural name. So let's say, so the first arrow in the machine learning literature is typically called as training phase. So how we turn the data into the decision is called training. Evaluating or predicting what happened for the performance is usually, I show it here in the second arrow, typically is referred to the test performance or test. So training phase, and this is the phase. And what we typically see as a difference between the past data point, past loss and the future loss is something that people refer to it as a generalization error. So how generalized from the past loss to what we see in the future. Once I started working with operations research community, I realized that people are somehow a little bit more creative with names here. So the first arrow, people call it prescriptive analytics, what is very much similar to training phase. The second arrow, they call it predictive analytics, and somehow it's very sensible names in terms of the role that these arrows have. But perhaps the most creative component is about this generalization error, where it came to me that they call it as post-decision disappointment. So that's how people refer to the different these errors that we have. Now, apart from these terminologies, what is at the heart of difficulty to talk about this post-decision disappointment or generalization error is how this object looks like. So the future loss is something that has is first of all formally speaking is a random variable, but what makes it particularly difficult about this random variable is that the source of uncertainty is two things. One is of course about the future sample that you haven't seen it. That's an obvious one. But there's also another source is about the training data set that you got it. So basically there are two sources of uncertainty. One is referred to the past and one referred to the future. And this is why if you open any statistical learning book, when you see the formalism around this future loss, you always see two layers of probabilities. So one is about the training data set and one about future data, sample. Now, let me a little bit elaborate more about how we measure this future loss. So there are different ways of looking at future loss, and this is typically translated in mathematical language by risk measure. And what risk measure means is how to look into how to turn a distribution into the real value to measure our performance. So the loss function in the future, let's fix our decision that we make. So it's a distribution, it's not one loss, it's not, it's a distribution that we encounter in future. Now the question is, how do you want to measure this future in the future? How do you want to measure the loss in the future? Here I'm going to name three very classical and popular risk measures. Arguably, the most popular one is expected loss. So you look at the expectation of the loss in the future. This is the most popular one in the statistical learning literature. You can take a perhaps most conservative perspective and you look at the worst case loss in the future. That's basically at the end of the tail, that it's a worst case scenario that you may face. And then there is a third one that I would like to highlight here is that something that people in OR operations research call it value at risk. It's a less stringent perspective comparing to two, and in the sense that you allow yourself to neglect epsilon probability of future loss. So you are happy with neglecting the very rare events, and then you ask the question that what would be the worst case loss if you allow yourself to neglect epsilon probability of future occurrence. So by definition, definitely the number 3 is something lower than 2, and the more the smaller epsilon, the closer to the worst case scenario. So these are 3 different risk measures. Which one do we care? It heavily depends on the application at hand. So if you talk about some learning problem, something that you want to actually think about the future loss repeatedly in the long run average, so typically the number 1 is the right criteria that you care about. But if it is some sort of safety critical problems or something that you really want to make sure that you hedges against any scenarios, you have to go with number 2. But there are some possibilities that, for instance, like problems related to health monitoring or anomaly detection, that you still are sensitive to false error or false alarm, but it's okay that if every now and then you have one or two false alarms, but still be highly sensitive to the errors, you can think about number 3. So each of them has its own application. It's not that one is better than the other necessarily. But if you want to talk about which arrow in the first part, which prescriptive analytics or training decision mechanism is important, I think this discussion is heavily tied to which risk measure you care about. So now in the rest of the first part of my talk, I just want to mention 2 different mechanisms about the training arrow, which actually develop based on which risk measure that we are interested in. So the general framework that I want to talk about is something that I mentioned earlier as distribution robust optimization. The distribution robust optimization, you can think about it as minimization, a worst case expected loss, in which the expectation runs over a family of distribution that people refer to it as ambiguity set. That's a very general framework. And the central piece into this framework is this set of distribution known as ambiguity set. What type of family of distribution you would consider, it immediately boils down to which risk measure you care about here. And there are numerous options here and for different type of risk measure. And typically where the data comes in is how to calibrate this data set. So this first arrow basically is how we exploit this data into this set of ambiguities. Now I'm gonna explain 2 very concrete examples to give you a little bit intuition about how this distribution robust optimization looks like. So let me first, by the way, before I forget, the connection to this future loss typically goes through the worst case expected loss. So this object that you see, you can compute this based on the data that you have. And the value of this worst case expected loss, sometimes referred to as certificate, is intended to be an approximation of the risk measure in the future that you care about. So basically, at the technical level, it boils down where J hat n is. So if you change the ambiguity set, the location of J hat is going to change. And basically, you try to say, okay, which one of these 3 items are important for you? And you try to make sure that J hat n would be a good approximation or a safe approximation of the risk measure that you are interested in. Now, if you might remember earlier that I mentioned that L has 2 sources of uncertainty, and one of them is about the training loss. That kind of conversation also is the same for the certificate here. What I mean by that is that actually certificate is not one value either. So that is also a distribution. And the distribution depends on which training data set that you have. So if you change the training data set, the certificate changes, and the type of let's say formal argument that you want to say is that where the distribution is located. That's basically at the center of statistical side of this data-driven decision making. So how this distribution is positioned with respect to the other risk measure is the statistical side of problems. So I hope I could picture how these high-level concepts look like in the context of data-driven decision-making. Let me just focus on these items and give a particular example of ambiguity set so that you have some concrete examples as well. So the first one that I want to focus is this expected loss here. So typically, this is the one that is very popular in machine learning problems related to supervised learning, for instance, and that's what you care about. One of the choice of ambiguity set in these cases is something that you can think about as a ball in the space of distributions. So this family of distributions actually characterized based on a ball in which you need 3 things, a center of the ball, a radius of the ball, and the type of the metric that you choose in the space of distribution. So these 3 things, once you have it, you can actually form this subset of distribution, and then you solve this optimization problem. Here now, there is another level of difficulties. If you think about it, this ball strictly speaking, is in the infinite dimensional spaces. The space of distributions are typically in infinite dimensional space. So solving this min-max problem by itself is difficult, but also just running over an infinite dimensional spaces can be another layer of difficulty. So there are some computational aspect to the first arrow here that could be introduces some challenges there. One of the popular choice of this ball is when the center is purely characterized by the data point that you have. So here it's where the role of the data pops in. So the input to this optimization problem, DRO, is basically the center of the ball. And typically this is an empirical distribution, where what that empirical distribution means is basically a discrete distribution where the weights are uniformly concentrated on this data point. So that's one choice, which happen to have nice properties with respect to the first risk measure. What I mean by property with respect to the first risk measure is that you can actually quantify where this distribution is going to be located, and not only preferably on the conservative side, namely J hat n would be a safe approximation of the future expected loss, but also asymptotically. So then as the number of data increases, you know how this distribution is going to concentrate it. So we also have that type of guarantees as well. So that's, let's say, a very brief overview of the results of the first risk measure. Now, let me give you a little bit background about the other two risk measures in which we might be interested in. And the question is, what would be an appropriate ambiguity set on these two? Given that the organizers of this talk are from control community, I thought that it would be nice to also mention that I think, to the best of my knowledge, it's fair to say that the credit for the result developed in this line of research is for control community. So there are people pioneered this line of research, Campi, Marco Campi and Giuseppe Calafiore, and also Garatti. They developed a number of results in this direction. And what basically they propose is that they pick up the ambiguity set as a finitely many distribution, and each distribution is just one Dirac distribution concentrated on one of the scenarios that we have. So this is what they call it scenario program, because you have n scenarios. Each of them is actually one distribution fully concentrated on one data point. And it turns out that actually this J hat n, defined in this way, has a very interesting property in terms of where this distribution is located. So by definition, we know that this value is going to be always less than number 2, but the question is more how it's going to be above number 3 and how close it's going to be to number 2 as number of data increases. From a mathematical point of view, this kind of min-max problem, this distribution loss optimization, is just a fancy way of writing minimization of the worst case loss evaluated on data points. So this basically what I have written here is nothing but that. That's what people in control literature call it scenario program as well. And here I want to highlight two results about this J hat n. If the loss function is convex in X, it turns out that just convexity in X allows us that J hat n is going to be rapidly concentrated on the right-hand side of number 3. That was the first result. And the surprising point of that is that this result is fully independent on the underlying distribution of the samples. To the best of my knowledge, that's the only result in a statistical learning literature that does not depend on any regularity of probability distribution. All the other concentration results required some sort of tail condition on the distribution, but this one is the only one that does not depend on any regularity on T. So this is a good result. I mean, let's say there's a very attractive result. There's another result that actually is a little bit more disappointing. I mean, it's actually on the disappointing side, is how fast J hat n is going to converge to this quantity, the worst case law. And it turns out that actually it's exponentially bad in the dimension of psi. And this, let's say, convergence behavior is exponentially bad, not because of an artifact of analysis, but inherently difficult. So there are examples in which no matter how you sample from distribution, it's gonna take exponentially many samples for j hat n to converge to number 2. So this distribution, funny enough, rapidly is gonna pass number 3, but very slowly, it takes ages to reach number 2. So that's actually some sort of very few minutes summary of the literature about scenario approach and the type of risk measures that people have studied in that literature. Now, I talked about computational complexity of the first arrow. I talked also about the statistical part. Now I want to talk about another problem that recently has received quite a bit of attention, and that I would like to call it as real-time implementation. And what does that mean? It means that imagine that you solve this optimization problem, whatever ambiguity set that you have, and now you get one decision. And now imagine that I give you a new data point. So I suddenly give you a new data point, let's say psi n plus 1, and then I tell you what would be your decision. The trivial approach is that just put it there and then recompute this arrow again. But that's not that's exactly what could be time consuming and not efficient, in the sense that the higher number of data points, the harder the task is. So what people start thinking about it is, can we have some sort of approximation of the current decision and the new data point that we have in order to find the decision in the next step? That's what we I show it by this, and this usually boil down to some optimization algorithm that you can solve it in real time. Just to flash back to this basic example that I said. So remember this curve fitting. So imagine that you already have this point. What this real implementation wanted to address is that now that I have a new data point, can I update my hyperplane together with this new data point without going through all the without processing all the other data points? Even though that this question has received recently a lot of attention in the context of online optimization, I would like to point it out that actually long time before, maybe even half a century before, people in control community also have looked into this kind of problem, and certain structure on L, like quadratic structure, allows not only to do it approximately, but exactly. A perfect example is Kalman filter. So in Kalman filter actually is an example in which we don't need to reprocess all the data point, but we just update it on the fly, and it's not approximation, but it's exact. What I wanted to now point it out, and as a summary of my first part, is that quadratic cos, convex quadratic cos, is a very particular case of convexity. And it turns out that actually not only quadratic one, but just convexity allows us to approximate this one. And what I personally found it interesting is that actually convexity helps addressing all these three questions for different reasons. And that's something that, in my opinion, I found it interesting. It's rather trivial to say that by now that the convexity helps for computational aspect, arguably is the largest class of problems that we can solve efficiently. But it is, in my opinion, non-trivial that the same property also helps for statistical side as well as real-time implementation. So what I'm going to focus in the rest of my talk is how this, I'm going to focus on this last item, real-time implementation. So I'm going to dive a little bit more into details to give you some updates about algorithm and some recent developments. But before I start the second part, I just want to tell you one piece of results so that you can connect it to here. And that is that in most of the popular optimization problem, this inner worst case expectation can be approximated or even exactly written as a separable loss function. So this worst case expected loss can be reformulated either exactly or approximately like a separable loss function, where in some cases, this FT has a very close form formula. It looks like something like loss function from some regularizer. And that's going to be the focus of my rest of the talk. So I'm going to talk about situation in which that you want to minimize a separable loss function in which each, let's say, term depends on the data point that you observe. And the question is, can you have a real-time implementation to solve these kind of problems? So that's pretty much the summary of my first part of the talk. And if there is no question, I can continue with a particular focus on this class of problems. Okay. So the second part of the work is I'm going to focus on this separable cost function, online convex optimization. This is a collaboration with my student Pedro Zattoni Scrocaro. He's the driving force and the brain behind it. I hope I can answer your question, but if I cannot, I guess he's in the audience and I point to him if I couldn't answer the question. So let me start with online optimization setting. So the first part, I just want to tell you what is the problem, what is the online setting, and then I continue with the algorithms and some results there. So sorry, I just want to have a look how much time. Okay, now I'm on time. Okay, so what is the setting? It's a sequential decision making in the sense that you make a decision. You can think about it like a game between two players, so to speak. So the first player, this green one, is ours, the decision maker. The decision maker make a decision, X1. Then there is some adversarial nature that is going to throw at us a loss function. So let's say I show it with F1 to connect to also earlier discussion that I have. Now, the cost that you incur is going to be the evaluation of the loss function on the decision that you make. So that's the cost that you pay. Now, based on this observation that you have, now you are allowed to make the new decision. And the new decision, based on this information, you make a new decision. Now, again, the nature is going to throw at you another loss function, and then you incur these costs as well. Note that there is a lag between the decision that you make and the loss function that matters. And this is really at the heart of this setting, and it's the important element that we are going to address. Now, this, you can think about it, it keeps continue like that, and then you make a decision in this fashion. So you make a decision at time xt, then the adversarial is going to throw at you a new loss function, and that's the cost that you pay. Now, if you think about at the end of the time horizon that you are implementing this, you ask the question how much cost you pay. Clearly, this is the amount of cost that you have paid throughout the process. So the accumulated cost that matters is this cost that you collected throughout the T steps. Now the question is it good or not? But based on the policy that you have to make a decision, and by policy I mean how you make a decision, the new decision based on the previous observations. You can think about it like that. So we benchmark this cost against something that typically we call it in hindsight optimal decision. So what we do is that we collect all these cost function that the adversarial throw at us, and then make a best decision in hindsight. But what is very important that this decision is fixed across all the loss function that you have observed. And then people call this gap as regret. So regret, in one sentence, is going to be the difference between the online adaptive decision that you make versus the best fixed decision in hindsight. So that's the quantity that is going to be the starting point of for us to make, let's say, performance assessment. Typically, we are interested, the lower the regret, the better, as it sounds from the name. But it is very important to point it out that the regret is not necessarily positive. The main reason that it's not positive because this quantity, that the decision variable changes over the time. So it might be the case that the cost functions f, t, do not share the same optimizer, and changing the decision variable actually helps in terms of cost. But anyway, that's the criteria that we have, and that's what we compare with. If I want to go back to the literature of control and I tell you which, for instance, problem this could fit naturally very well, you can think about system identification. So think about the system identification, that there is some true data generating model, and in hindsight based model is really what you are interested in. So you want to find a model that is describing all the data points. So it makes sense in system identification problems, or you can think about it supervised learning if you're not familiar with the sysid problem, that's really the case that you care about. So if you are comparable with this, you are happy with. That's a good example. I have to say that when I saw this framework for the first time, I thought that it's very natural to connect it to the control problems as well. And I have to say that I didn't appreciate much at the beginning the work on that line, in the sense that I thought it's immediate to connect this framework to the control problems. But after a little bit work, I realized things are more non-trivial than I thought. And I thought, because of the audience of this group that might be that are more from control background, it's good to touch some connection of this problem to the control problems, to highlight what are the non-trivial challenges that you may face if you want to apply it to a control problem. So let me go back to a control problem for, let's say, for the next 5 minutes. I'm just going to focus on how a control problem can be mapped to this setting. So the first attempt is that we think about the decision that you make is exactly the decision that you make. So the control action. So you can say, okay, I want to use an online optimization technique to tune my controller. Now, if you do so, and then think about a classical linear system, and then look at what the regret suggests. If you look at the regret, you collect this accumulative cost in the time horizon. But the second part, if you think about what is the meaning, you see that the meaning means an open loop control. That's something that we are typically not interested in. So the regret, the meaning of regret is somehow not useful if you define these actions as the direct outcome of the control actions. So this is the first problem that you immediately face if you want to use regret concept in a control. The other one, which is much more problematic, and I think it's really at the core, it's going to be the main difficulty to map this, is these loss functions. So if you think about it, this FT loss function, let me focus on the first part. This loss function that you encounter are functions of state of the system. Typically, the cost that you collect depends on the state of the system, which in this case is driven by this sequence of actions. So FT-UT has a very meaningful object for us. But having the same FT for another controller is totally meaningless for us. So if you want, again, to look at the regret, the sequence of cost function that you observe are not going to be the same that is driven by this minimization there. So all I'm trying to say is that the direct application of the regret in the control context is going to be difficult, and it's going to be a challenge. And people like Elad Hazan and the others developed some mechanism to address these two difficulties. And here I just want to very briefly and superficially touch the technique. So there are three steps to address these two challenges. The first one, and perhaps the easier one, is how to deal with open loop control. So what we do, we actually give a structure to the controller. The particular structure of interest is disturbance feedback. So not a state feedback, but disturbance feedback, because the convexity is very important for us. So you can think about as the first action is you generate the U of t based on a feedback of the disturbances that you have observed till that point. So the decision, the sequence of decisions are no longer the action itself, but the parameter of the feedback policy. That's the first step. The second step is that if you think about this, you see that as you go further and further, the number of decision variable increases because the feedback that you collect from the whole history is gonna increases. That's something that we typically want to avoid in any learning context. So we want to have finitely many parameters. So what they do, okay, obviously we cut the tail. So we say, okay, I'm not gonna have infinite memory. I'm just gonna have finite memory from, let's say, past H samples. And so the feedback is gonna be depending on H. This is what they sometimes refer to as a finite memory. You can only do that if the system is stable. So you have to assume that the system is stable to be able to do this without causing much violation. And that's the, if you want, you can think about it as a limitation of this step. And then final step is that to adapt the regret concept that I said earlier to something that allows for memory. So previously, the first, if you had seen it before, this is immediate, but if this is the first time that you see the regret, it's probably hard to digest what I'm saying as the third step. But at the core is that the sequence of decision that you make previously, each one only influences the cost function at that time, but now you allow that each different decisions that you made also contributes to the cost at this moment. So this is kind of the third step. And I thought that it's worth mentioning these three steps that people develop in order to fit control problem to online optimization. Okay, so I hope I described the online optimization setting for you. I hope you already got a little bit intuition and insight about the concept of regret, and a little bit effort here to how to map a control problem into this. Now, let me switch gears to the algorithm. Actually the main message of this context is how to devise an algorithm that enjoys regret bound. When I'm talking about algorithm, basically I'm talking about this function. So how you get the current decision and let's say previous loss function and make a next step decision. Before I tell you how this works, let me go back to some very basic optimization algorithm that we know probably since undergrad. So the first algorithm that I want to touch it is the classical gradient descent. And I call it explicit gradient descent for a reason that is going to hopefully be clear in a minute. What is a gradient descent? Is that you start from x of t, you look at the gradient of a loss function. For the time being, think about one loss function. You take a gradient, you move with a step size eta, and then you see what is the next step. That's the one that we all had seen it in undergrad, perhaps. And that's how we make a decision. Update our candidate for the optimization algorithm. And we know that under certain conditions, in part for convex functions, if the step size is sufficiently small, in particular the Lipschitz continuity of the gradient, 1 over the Lipschitz continuity of the gradient, which is known as smoothness parameter, this algorithm globally converges to the optimizer that we are interested in. And the point is not only that it is a sufficient condition, it's actually also to some extent with a little bit more conservative version, it is necessary as well. So if the step size is too big, then this algorithm does not converge. In fact, it diverges. So kind of inherent limitation on how fast you can move with this algorithm. And not only about the step size, but also convergence rate. So you have fundamental limit on convergence rate and fundamental limit on step size. So this is about the first algorithm, the most classical one. Then there is another version that people refer to it as an implicit gradient descent. And if you want to see what is the difference, perhaps it's easier to see in this equation. The only difference is the evaluation of the gradient. So here is gradient at time t, here is a gradient of t plus 1. And It is called implicit because you cannot write one-line equation in a computer and hope to be able to run it, because you cannot run it. You have to solve it implicitly to be able to do that. But let's say you somehow manage to do that. What is interesting, so what is the meaning is that the gradient on this point that you are is not important. What is important is the gradient of the point that you land in. So where you land in here, the gradient is more important than where you are. And what is interesting about this algorithm is that there's no limitation about convergence rate and neither a step size. So you can actually, this algorithm converges for any step size. And as a matter of fact, the bigger step size, the faster the algorithm. So it's kind of interesting feature of implicit gradient descent. But of course, you pay the price somewhere else. Solving this equation is the price to pay. But the main reason that I pointed out is that there is a very important take-away message here, is what I said earlier, that hopefully this is convincing enough for us to know that the gradient of the next step that we land in is more important than the gradient of the current position that we have. And this simple observation was actually the birth of a new algorithm. They call it extra gradient descent. And what does the extra gradient descent do is that, maybe it's hard to read from the equation, but it's very simple step, is that you are at this point, you take one step based on the gradient of the function that you are interested in, you go to the next step. Here you look at what is the gradient of the function, and you take your next step according to this gradient that you already observed in the next step. So in a way, this extra gradient descent hopes to reconcile this difficulty of the implicit equation by going one step and look at the gradient here and take it from here. There are some results regarding this extra gradient descent and how it's going to be helpful for a subclass of optimization problem. I'm not going to discuss that one, but all I wanted to tell you is that think about these three basic optimization algorithm. And now I'm going to switch back to the online optimization, and I'll tell you how people use these things in that context. So let me go back to the online optimization. So the most, let's say the first algorithm that people start looking at it in the context of online optimization is the so-called online gradient descent. And what is this? Is just basically classical explicit gradient descent. There is some projection here if you also have constraint over the cost function. But apart from that, this is just simply gradient descent that I mentioned earlier. And it turns out that gradient descent is so powerful in a way that it's actually so robust that this regret can be controlled by the square root of the growth rate. So you remember that the regret was summation of all the costs that you collect minus the best in hindsight. And if it is sublinear, in particular square root of t, what you can conclude that average regret is going to go to 0, and which means that the more data that you have, the better decision that you make in terms of regret. And of course, there is a particular guideline on how to choose the step size. Now, what is added to this context and is also partly the focus of the talk that I want to say is that what if you have additional information? So far, you're totally blind to the cost function that occurs at the time that you make a decision. Now, imagine that you have some piece of information about that. And the question is how you can exploit this information, how you can actually improve the algorithm based on some sort of information that you have about current cost. And this is the focus of also this work that I wanted to explain today. So the algorithm, the first algorithm proposed in this context was developed by Rochlin and Sridharan. So what they propose is, it looks like that. Again, I guess it's hard to understand what's going on here, but if I give you the geometric picture of that, it's exactly extra gradient. So the extra gradient descent, in the sense that we make a decision, we make a step based on this character m of t in the algorithm. We look at what's the gradient of the previous losses there, and we take the we take the next step based on the previous gradient descent. This extra gradient descent turned out to be very powerful to exploit the information of the current loss function. And how people formalize it, let me explain it in a little bit more detail. So this is the algorithm that I explained. So this algorithm here is exactly this one. The key question is how to tune the step size. And what Rochlin and co-authors suggested is to actually choose the step size in this fashion. So what does that mean? So if you look at these step sizes, what it means is that you look at the difference between the gradient of the function and the mt that you put it here. Think about m as a whatever that you pick up. You can pick up however you mt is. You plugging in this formula up to t minus 1 and look at how far your mi is from the gradient of the function in the past, and based on that you make a step. And what is interesting is that the regret is also characterized based on the same criteria. So based on the mistakes that you had, or let's say the mismatch between the character mt and the loss function, the gradient of the loss function, you can actually characterize the regret. Now, let me give you a very degenerate, very, let's say, extreme example. Imagine that m, the character m, is exactly the gradient of the cost function that you have. Remember that here at the t plus 1, you need gradient of f at t plus 1. That's exactly the information that in the initial setting you didn't have. But let's say you would have it. If you would have that, if you would have this information, the regret becomes constant. So this term goes away fully, and the regret is constant. So it means that actually by having this information, you solve the problem without any regret up to a constant. And what could be also interesting to see that actually the step size goes to infinity in a way, in the sense that this becomes smaller and smaller, and then the order of the step size, it means that it can become arbitrarily large. But that's not really surprising in the sense that if you have a closer look at this equation, if you put the mt as the gradient of ft, you see another update rule in the same fashion as implicit gradient descent. So long story short, deep inside this algorithm, if you want to operate it in an ideal way to have the minimal regret, what you need to do is that to replace mt as an approximation of the gradient of f at time t as well. But then also you need to solve some sort of implicit gradient descent. So when the moment that you observe that this is implicit gradient descent, you probably no longer surprised that the step size could be arbitrarily large. So connection to the implicit gradient descent that I mentioned. Now, in this context, the work that we propose is to try to circumvent this phenomena of implicit gradient descent. And the small modification that we did into the algorithm are those green parts. So the green parts that you see here are the small modification that we did to the Rochlin's algorithm. So what we did, first of all, we make the step size conservative in the sense that we have some constant term here. If you would be interested in what beta means, it's the smoothness parameter. Then instead of evaluating gradient of f at step I, at the xi, we compute the gradient of f at step y. And basically what it boils down, that mt, now it just suffices to be the prediction of one step before, which means if you look at this algorithm in the ideal setting, it looks like an implicit gradient descent. So if I want to just say one sentence, is that this modification into the algorithm allows us to transfer from implicit version to an explicit version. And definitely we have to also pay the price, or let's say we have to modify the step size and regret bound accordingly as well. So that's basically the takeaway message here. There are some extension to this algorithm in terms of non-smoothness and also dynamic regret, but these are details that I refer to it in the end. But that's pretty much the suggestion that we have. Now, in the last part of my talk, the technical part, I just want to give you a little bit overview of the technical results in this literature. So this is the algorithm that we propose. We deliberately put the M character, I put it the gradient of F tilde to remind ourselves that this is meant to be the prediction of the loss function at time t+1. So at t+1, you have to make a decision. This is the prediction that you have. And this dt, which represents the error of the prediction that you had in the past, is going to help us to tune the step size. So this is the table of the result. This is just a summary of everything that I had told you so far. So this is let's say the general prediction. So this whatever that prediction that you have, you can put it here. The step size should be determined based on the collection of the prediction errors that you have in this fashion. And the regret that you have is going to be also the square root of this collection errors that you have. The good thing about this result that we are presenting here is that it can be actually, it can retrieve the two results in the literature as an extreme scenario. So the first scenario is that you don't have any prediction. So what you do, let's put the gradient of F absolutely 0. If you put like that, if you carefully look at the update rule, it becomes classical gradient descent. The step size, then you start collecting a constant error, which means that the step size becomes like 1 over the square root of t. So you also retrieve that step size rule, and the regret is also going to be sublinear square root of t. The other extreme is that you know exactly the gradient of F. And that's the recent work by Fatma and her student in 2019, relatively recent by now, 4 years ago, in which the gradient is exactly that one. The step size they propose is going to be constant step size, and the regret is going to be constant as well. So that's another, let's say, extreme point in terms of full observation that we have. There are a little bit modification of this if instead of convex loss, you happen to have strongly convex, then this part can be modified in a way that the regret turned out to be the logarithmic one. And that's also, but this is kind of a standard technique when you go from convex to strong convex. So you can actually modify the step size so that you ensure logarithmic regret. So that's pretty much the theoretical results that I would like to present now. I look at the, can I talk for a couple of more minutes for some real example? So we implemented on some real data. Can I continue, João? Okay. So I just want to show you one how this online optimization look like in practice, and let's call it online optimization in action. So the case that I want to present is the classical portfolio optimization. It's a very, let's say, classical example in financial operations research. So what is the setting? You have n assets. These assets, you want to invest in that. Your decision is how much of your money you want to invest in this particular asset. So you have n decision, each of which represents the let's say percentage of your capital that you want to invest in a particular asset. That's what you would want to do. What is the catch, or what is the difficulty, is that you don't know what is the rate of return of the asset. So you first put your money, and then tomorrow you come back and see what happened to your money. That's represented by the so-called rate of return. So you can think about this R1 is, let's say you put $1, you X1, you put $1 in asset 1. Tomorrow, your money is going to be R1. So that's what is called rate of return. So that's a perfect setting for this online decision making, that you always have one lag behind the uncertainty. And what would be your total wealth is simply the summation of xi ri, or the inner product between the vector of the rate of returns and the decision that you make. So that's going to be the total wealth after one round. And if you think about it, you can think about that you go to this market and put your money, and each time you trade your money based on the algorithm that I just told, and then see what happens. What would be our loss function? Clearly, we want to maximize this one. But it's well known that optimizing this inner product itself is very risk neutral, and it's not a good idea to optimize this. So what usually people propose is so-called log utility function. So minus logarithm is a monotone function, so it doesn't change the optimizer, but the minus one is what we want to minimize. So we want to maximize logarithm or minimize minus log, and that's the function that we consider. And now, speaking of prediction, what you really need in everything that I said today is what would be the gradient of this loss function. So if you look at the formula of this f of t, if you look at the gradient looks like that, where RT here is your prediction of the rate of return on the step that matters. Okay, so this is the loss function that we care. Let's say you have a prediction of the rate of return. Either you are fully oblivious, or you have full prediction. That's what I want to show you next. But that's the setting, and in the algorithm that I told you, we implement this as the prediction of the gradient. Now let's see how it looks like with real data, actually from exactly New York Stock Exchange. So this is the data set that we use. We examined 4 scenarios, and among these 4 scenarios, I think I want to highlight 2 interesting points. At least for me, it was very interesting. So let me start from the trivial one. The trivial one is the perfect one. So you know the rate of return, and then you invest. Had you been able to have this option, you would have been rich. But let's say you know exactly the rate of return. The blue curve is going to be what happened to your wealth in a positive way. So this is how the wealth is going to grow, and no surprise, it's just getting improving. The main reason that sometimes you see a little bit, the main reason that is non-monotone is the fact that the gradient descent is not intended to be monotone. The algorithm is not intended to be monotone behavior. So a slight increment is because of the gradient descent dynamics. So this is the blue one. Now, what I want to point it out as let's say a basic benchmark is that, let's say you have no idea what is the rate of return. And by no idea, what I mean is just a random variable. So we pick up totally random variable. It's just uniform between 0 and 2. We put it in the algorithm and see how it looks like. So this total nonsense random variable, when we put it into the prediction, the orange one looks like what you see here. So basically, sometimes you gain, sometimes you lose, but it's probably around 0. You remember that it's log utility. 0 means 1, which means basically you don't lose, you don't gain, nothing. So the algorithm somehow is robust with respect to 0 prediction. So that's how your money looks like. Now I want to tell 2 funny things. The first one for me is when you try to outsmart the market. The market, when you outsmart, what I mean is that what would be the most reasonable, or let's say what would be the first guess to predict rate of return? The prediction of rate of return is just the previous one. So think about that, you pick right now, the rate of return and treat it as the rate of return tomorrow. The red one, what you get out of the algorithm is the red one. So it's going to be the worst possibility. So you're going to be worse than the random one. I personally found it very surprising. So just one step lag makes it worse than total random prediction, which probably shows how the market has certain feedback into that, and you cannot really have a elegant prediction. The second observation is a kind of cheating, but it's interesting to see how it works. The green one. What is the green one? The green one is that, okay, we cheat, we look at the R of T, which is the current rate of the return, but we put an unbiased noise on top of that. So it's a, let's say, unbiased prediction of the rate of return. And it works quite well. So if you happen to have unbiased prediction, still you can, with some variance, you still benefit from the trading in the market. But of course, the catch is that who knows what is the unbiased prediction. And if you had it, I guess if you have any good unbiased prediction, you would be rich. Okay, so that's pretty much what I wanted to present. Just two very short points about extension of the work that you can find it in the paper is that everything that I told today was about smooth function. So you can actually go to the non-smooth function by the classical techniques from composite mirror descent. So we actually augment the algorithm in order to incorporate the non-smooth part as well. And then there are some extension toward dynamic regrets. And that's also a possibility that has been reported in the paper. So with that, that's the references that related to everything that I told today, and the red one is the main one that I mentioned. And thank you for your attention, and I'm happy to take your questions.